Okay, so we have discussed about this Bernoulli's equations and the real world application of Bernoulli equation. Okay, so another like also we have discussed about viscosity, the concept of terminal velocity, and all that. What does a viscous fluid mean and all that. Okay. Um, Another very important property we have discussed in previous session on surface tension, but we have not discussed about the real world application of surface tension. So we will discuss about that very important properties of fluids, that is surface tension. Okay. So uh, actually there are two forces when like say, let me say this is my container. Okay. So this is a container. Okay. So I have water in it. Okay. So so this is my water inside it. Okay. So you consider one molecule inside the water. Okay. So let us say you have a molecule inside the water. Okay. So this molecule, it will be like there will be neighboring molecules. Okay. So it will be uh, so because of molecular attraction will be there, and the neighboring molecules, it will this the neighboring molecules, there will be a force, like molecular force between the neighboring molecule. So there can be molecules like this, and the force is like this, force like this, some forces like this. So in this kind of a situation, this particular molecule is completely balanced. Okay, but you imagine a molecule at the surface. Okay, so let us say you imagine a molecule at the surface. Okay, so this molecule, it will get attracted by a molecule which is below. Okay, and also there will be force in this direction, there will be force in this direction, like this. Okay, so finally it will be kind of a semicircle like this. Okay, so you have a semicircle like this. So what happens, the surface of this liquid, it will be in a state of tension. Okay, why it will be in a state of tension? So let us say, let me take three molecules. Okay, so let me take three molecules. Okay, so this molecule anyway will have a downward force. Okay, so when it is being pulled downward, here you have a force like this, and here you will have a force like this. Okay, so when this molecule is being pulled downward, still this, suppose you have the center molecule is being pulled downward. Okay, so now when it is getting pulled downward, this molecule is not allowing it to move downward. It will try to pull it back. Okay, similarly you will have another molecule, so it will be in a situation like this. Okay, so the final equilibrium condition, so finally it is in a equilibrium condition only. Okay, so the final equilibrium condition will be something like this. You have a downward force, and you have, like say, you have two upward forces like this. Okay, so you have two upward forces like this. Understood? So when you have one downward force which is pulling it down because of the cohesion, which is because of one molecule lying downward, and here you have one molecule, here you have another molecule, and here you have one molecule. So it will be in this kind of a condition. So this kind of, so what will happen, like say, let's say this is a force F, and let us say this is force F1 and this is F1. Okay, and let us say this is my angle theta, right? So this my F is equal to like say f2 sine 90 minus theta, so it is sine theta. Okay, so it will be two forces, two component, 2f2 sine theta. So like that, in this condition it will be remain balanced. But if you see, like the surface molecule is in this kind of situation. Okay, so three forces acting on this. So finally, in the balanced condition, you will see your surface, because forces are acting like this, so it will behave like a stretched membrane.
Understood.
So stretched membrane, so this surface will be like this. So you will have because of these forces, because this force acting like this, so like these forces are there, that's why it will be like a stretched membrane. Okay, so it can be like this for liquids like water. Okay, but for liquids having higher surface tension, that we will discuss, it can be like this also. Okay, so your surface can either be concave, or your surface can be concave or convex. So this is your concave and this is your convex. Okay. So this kind of situation. Because surface tension is a property of a fluid, because of which because there is a imbalance force on the surface, so the surface will be in a state of tension. Okay, that's why it is called surface tension. Okay, so so depending on the surface tension, so surface tension is a property. Okay, but like say there are two types of forces. Okay, one is your called cohesive force. Cohesive force you might have studied, and another is called adhesive force. Adhesive force. Okay. So this cohesive force is the force between similar molecules. Similar means water. You have water. So water to water molecule. So let us say you have let us say you have a capillary tube. Okay. So you might have seen it will form a meniscus like this.
Yeah.
Okay. So this molecule, and this molecule. So the force between these molecules, this is called your cohesive force. Okay. So this force between similar molecule. Okay. Is a force between similar molecule is called cohesive force. Cohesive force. Okay. And but between this liquid and the glass, so let us say this is glass. Okay. So between the liquid and glass, so the force between dissimilar molecule is called adhesive force. Okay, adhesive force. Okay. So if the adhesive force is more, then it will form a concave surface. If the cohesive force is more, it will form a convex surface like mercury. So we might have, this is like say water. Okay, so you have water inside this, so it will form a surface like this. Okay, it will form a surface like this. So this is for water. But if you have mercury, instead of rising, it will go down. Okay, so it will be, you have mercury and mercury, so it will here, so it will go down like this. Okay, so there it will dip. Okay, so here this is the capillary rise is this value, like this is your capillary rise here. Okay, but here this is a drop. Okay, so you have drop. Okay, in case of mercury. So why in case of mercury it goes down? Because in mercury the cohesive force is more, whereas in water the adhesive force is more. Okay, so and the higher is the cohesive force, higher is the surface tension. Okay, so that's why we call surface tension is more for mercury and less for water. Okay. After all, what is cohesive? What is surface tension? Surface tension is nothing but the intermolecular force. That's it. So surface tension is otherwise called the tensile property, tensile strength of liquid or the fluid. Okay. Suppose I am saying steel has more tensile strength. That means the molecular force between steel molecules is more as compared to aluminum. Let us say I am saying steel, the tensile strength is 700 MPa. Aluminum, the tensile strength is 400. That means steel molecules, intermolecular force between steel molecule is high. So that's why steel tensile strength is high. Okay. In case of fluid, again surface tension is otherwise called as the tensile strength of fluid. So surface tension is a property which is otherwise called as the surface tension of the fluid, tensile strength of the fluid. So surface tension is tensile strength of the fluid or the cohesive force. Okay, because it is in between the similar thing. So so for mercury, the surface tension is more. That's why the cohesive force is more. So in case of water, it is less. That's why this glass is attracting it. Okay. So so now this surface, because of surface tension, what are the different phenomena, real world phenomena that can happen? So because of this tension, the fluid will behave like a stressed membrane. Okay. So so if you put a needle, there are chances that it will float. Okay. So not going into buoyancy because of surface tension that happens. Okay. And you have studied that surface tension is equal to, surface tension is normally written as sigma, is equal to F by L. Okay. So what is this F and L? Okay. So let us say you have this. Okay. So now let us say you are looking from the front. Okay. So let us say this is a cylinder. Okay. So from the front you can see it is a circular one. Okay. The circular one. So if you see draw, you put any line here. Okay. Let us say you have put a needle here. Okay. So this needle, there will be some forces acting on both sides of this. Okay. So this forces acting. Okay. So when the forces are acting, so let us say the length of this length is L and force acting is F. Okay. So the surface tension is equal to F by L. Okay. That is how the surface tension is. Okay. So on the surface, always there is two forces acting on both sides. Okay. So the force acting on it divided by length is called your surface tension. Okay. So clear? Okay. And also you might have observed, suppose you have a soap film. Okay. So you have a soap film. You can see it is, let us say it is like this. Okay. You have a soap film and you have some kind of thread like this. Okay. So you have a soap film and you put a thread here. Okay. So circular thread means this irregular shaped thread. So if you just put a needle on it, this film will get removed. So because the forces are acting outside, earlier inside force was there. Now that force, only outside force is there. So because of this force acting, after some time it will become circular, because so this will become circular. It will become circular because of surface tension, the fluid surface always want to attain minimum surface area. So as compared to this has minimum surface area. Because of this pulling from outside, it will try to attain minimum surface area. So raindrop, why it try to attain minimum surface area? Because the lesser is the surface area. Like for a given volume, it will have the sphere will have lowest surface area for a given volume. say for a given volume we can make a cube, we can make a like a different types of you can make a cylinder, but the sphere will have the least surface area. That's why the liquid raindrop and all they try to maintain spherical shape, because they want to make the surface area minimum. Okay, so why surface area minimum? Because at the top, because of the imbalance force there, because when there is imbalance it will have more energy. Suppose you are imbalance, that means there you have more energy, but as per nature's principle you want to maintain the minimum energy state. So to maintain minimum energy state, it will maintain minimum surface area. Okay, so clear till this point? Okay, I'll take a picture. Okay. Okay. So we will take some typical values of different surface tension values, which is nothing but your cohesive force. Okay. So you have water, which is your H2O, and the surface tension. Okay. Surface tension. Okay. So the surface tension value for water is 0.075 Newton per meter, because you know force per unit length. Okay. Similarly, the soap solution, its surface tension is 0.03. Okay, 0.03, almost half. Okay. So and mercury, okay, mercury, and it is Hg. Its surface tension value is 0.4. So almost 10 times. Okay, 0.4 Newton meter. Oh, that means mercury has 10 times more surface tension or cohesive force as compared to water. That's why the intermolecular force between the mercury molecules are very high. That's why if you drop a mercury, it will not spread. It will not wet the surface. Instead, it will behave like a solid ball kind of thing, because there is lot of cohesive force. That's why it is behaving almost like a solid mercury. So the important thing is between water and soap solution. Okay. So when you mix some soap detergent powder, when you mix with water, its surface tension will decrease. Okay. So when the surface tension decreases from 0.07 to 0.03, it will because of lesser surface tension, what is the cleaning process? The dirt get accumulated inside the small pores in your clothing. Okay, or when you are washing your face, there are some your face has some pimples and pores and all. So the soap solution will enter into the pores. So it will enter or weight your surface more when the surface tension is less. Okay. So by using your soap solution, because its surface tension is less, it is able to weight your face much better as compared to normal water. Okay. So by adding soap to the water, whatever soap solution you are preparing, its surface tension is less. That's why it is enter into the small pores. It can clean the clothes, it can wash your face and all that. Okay. So that is the important. And another very important real world phenomena is like the soup. Okay, you will find your hot soups very tasty, right? Or any soup or any even hot food, it is very tasty. But when it is cold, it is not tasty. Why? Because at higher temperature, surface tension is less. Okay. So surface tension sigma decreases with increase in temperature. Okay, so let us say your soup. Okay, it may have surface tension say 0.07 Newton per meter. If it is like say 60 degrees centigrade or whatever, it may come down to 0.05 Newton meter or whatever. So with decrease in surface tension, it will spread completely. It will weight your tongue like anything. Okay. So when you it will spread your tongue, so you will find it more tasty. Okay. So that is another real world example of interpreting surface tension. Okay. So surface tension, you just remember that it is nothing but the tensile strength of the fluid, like tensile strength of the solid, like this is also cohesive force or the tensile strength of fluid. Okay. So that is the real world and okay. Okay. So another important thing related to surface tension is capillarity. Okay. So capillarity, we will just discuss what is capillarity. Okay. So, capillarity is rise of fluid in a very capillary tube. What is capillary tube means tubes of very less diameter. Okay, so the capillarity phenomena you will observe in small diameter tubes. Okay, so let us say I'll draw two cases. Okay, this is one case when I have water, and in another case when I have mercury. Okay, so this is water. Okay, and this is water, and it will look like this. It will be looking like this, and let us say I have another pot. Okay, so I have this, and I have this. Okay, and it will be like this. Okay, so this is sorry, this is kind of. Okay, so this is your mercury. Okay, and here this is my capillary rise. You can say uh, this is my capillary rise, the height. Okay, and here this is the capillary drop. Actually, it is not rise. So here you can say this is your drop. Okay, like it is going down. Okay, so this is water, and this is mercury. Okay. So how do I derive the formula for capillary rise? So it is like this. So because you have surface tension acting, okay. So this adhesive here, the adhesive force is more than that of cohesive force because this is water. So you have a surface tensile force T acting like this. So you have T and you have this one, T acting like this. Okay. So this is T and this is T. Okay. And let us say this angle is my theta. Okay. So I have T cos theta. Okay. I have T cos theta, and let us say this is 2T cos theta. Because 2T cos theta. Okay. And if you consider this meniscus only, so this is your meniscus, and let us say this is my height. Okay, so this is my height or whatever. So yeah, so if you look from the front, this surface tension, it is acting on a circular, like it is acting on this circle. If you see from the top, it is acting on the circular this thing on that much length it is acting. So what is that length? That length is 2 pi r, right? 2 pi r, and then the surface tension acting on it is 2 t cos theta. Right? T cos theta is the force, upward force acting. Yeah. Is equal to the weight. Okay. So let us say H is capillary rise. So it will be pi r square into H. Yeah. Okay. So I want to find out what is my H, right? So pi r square, that is the volume, right?
Pi r square into H is
volume. So I have to multiply it by density into G. mg na? Volume
mg
into density is equal to mass into this.
G.
So then my H will become, like say pi cancels, right?
R also cancels.
So 2r, okay, 2t cos theta
by pi r rho g.
pi cancels.
Sorry, by rho g.
Rho g.
Rho g r.
No, r, rho g r. Okay. So okay. So t cos theta divided by rho. Okay. T cos theta rho g r. So it is 2t cos theta. So here don't confuse it. T cos theta acting on the whole thing. So don't put 2 there. So 2 pi r into t cos theta. So your capillary rise is equal to H is equal to 2t cos theta, right? Divided by
rho g r.
2t cos theta divided by rho g r. Okay. So what do you understand by that? If r is less, your capillary rise is high. So with small tube, very small diameter tube, your capillary rise will be very high. Okay. So in case of, so it depends on theta. Okay. So in case of water, this theta will be almost zero. Water, you will not see this kind of meniscus and all. So you will this kind of situation will give rise to, you will have a positive term. Okay. But with mercury, this theta is negative. Theta is more than 90. So with mercury, theta is equal to, let us say, 140 degree. Okay, so you will end up with cos 140, which is negative. That's why you will have a depression there. Okay. So now you understand like capillary thing, capillary rise, and that force per unit length, and understanding the adhesion, cohesion. These are some of the key takeaways of properties of fluid under surface tension. Okay, and another important thing, capillary tube is like your trees and all. Okay, your root. So the water flows from bottom to top to leaves and all through these root, which are very small capillary tube. So because of capillary action only, it flows throughout the tree, it reaches the leaf and all. Okay. So these are some of the important applications of real world applications of capillary action. Okay. I mean surface tension. Okay. So yeah, so there are mainly the one is dependence on temperature. So with increase in temperature, surface tension decreases. That's why your soup will be tasty. And then the second application is the adding detergent to your water, and your surface tension decreases, so better cleaning. Okay. Then you why the liquid drop is spherical in nature, because of the cohesion. Okay. Then soaps and detergents, and then washing with hot water. So washing with hot water is more effective than washing with cold water, because surface tension decreases. Okay. So that's why that is also, you clean this baby clothing and all, you clean with hot water. Okay. So that will disinfect. Okay. And in this capillary action, what I have explained already. Now capillary action, and then formation of meniscus, that I have explained, because of adhesive force, formation of meniscus, and so these are some of the important real world applications of surface tension. Okay. So we have discussed earlier the mathematics, that the pressure difference and all that on a soap bubble and a water bubble, and those derivations we have already done. What was my intention was to explaining the physics and the real world applications of surface tension in this session.